be given a problem like we just gave you, and for them to tell you to calculate the pressure of the gas at the end of the reaction. Because now you should know how to do that. But before, they wouldn't have done that because you didn't know how to calculate that now. So if you don't have those written down already, or then you should know those. I'll give you a second. I want to take a picture. All right, looks like we're all good. Let's go back to that problem now. Let's go work it out. So we said it also produces CO2. CO2 is going to be our gas, water is going to be our liquid, and this is going to be aqueous. If we're assuming this is done in water. Water is our solvent. All right, so what should we do next? We wrote out our chemical equation. Yeah, so we need to balance it now. So what is the balanced formula for this? The 2 here, see what we do. 2 here. 4 here. 2 there. Or that can just be reduced down to like 1 to 2 to 2. Check if I'm right. That looks right. Okay. Is that all good? Are we all balanced left and right? Let's see. I'm going to do what Rich does. Got 1 calcium, 1 calcium, we're good. 1 carbon, 1 carbon, we're good. 3 oxygens, 3 oxygens, we're good. 2 hydrogens, 2 hydrogens, we're good. 2 chlorines, 2 chlorines, we're good. All right, so that's how make sure that you balance it correctly. So next, what do we do now? We have our balanced chemical equation, and we're given this reaction, and we're given information about both reactants. Again, just because certain things we learned earlier on doesn't mean that they cannot come back to bite us, right, Rich?
Lovely molar ratio.
Okay, no, we already we already did that in the chemical equation. But if we're given the information, calculate the mass or the moles of both reactants, what does that mean for how much product we form? What should we be looking for? Anyone?
All of those.
How'd I condition y'all? If we're given the information about 2 reactants, we should be limiting reactant, yeah. So in this case, we're given the information about hydrochloric acid, right? Because we're given the volume and we're given the molarity. That means we can calculate moles of hydrochloric acid. That's something we got to start being able to see quickly when we see volume and molarity. That's moles instantly. And then grams of calcium carbonate. We know just using the molar mass, we have the moles of calcium carbonate as well. So we have to figure out which one the limiting reactant is. So let's go ahead and do that. So let's start with 50 grams of calcium carbonate. What is the molar mass of that?
100.
100 grams.
0.09.
Okay, 0.09 grams for 1 mole EaC3. Then we use the mole to mole ratio because, and what product are we trying to go for?
CO2.
CO2, right?
It's a gas.
Yeah, because we only care about the gas that's being formed because the question's asking determine the pressure of the gas, right? So we know that if we're going to convert to any product, it's going to be the product of CO2 because that's our gas. So there is 1 mole of calcium carbonate for every 1 mole CO2 that's formed. And we can just stop there. Doing that, you probably get about 0.5 something. What? 0.49?
Yeah, 4.9.
9, okay, that'll work. And now we got to do that for the other part. So we have a 0.5 liter solution of 2.5 molar hydrochloric acid. That'll give us about 1.25 moles of HCl. And we take that and we do the mole to mole ratio. So now this one is 2 moles of HCl. 1 mole of CO2 is produced. And we're good there. So we just divide that by 2 again. So what do we? 2.5 carbon dioxide. All right, so based on that, you can figure out which one's the limiting reactant. So which reactant is limiting?
Carbon.
Carbon?
That's less. Wait, oh, no, it's
calcium carbonate.
It's that.
Carbon is our limiting reactant, is what you said?
Calcium carbonate.
Calcium
Yeah.
carbonate, right? Yeah, so calcium carbonate is our limiting reactant. So then whenever we find our limiting reactant, we can cross out the other one, right? Because we don't want to confuse ourselves. Now let's do another color. Actually, we don't have to. So we're asked to figure out the pressure of the gas in the container after the reaction has gone to completion. So how would we go about doing that? PV equals nRT, right? Because we're not given a before and after scenario, right? I mean, yes, there's before the reaction happens and after, but we're not given like the information of a gas before the reaction and after the reaction. That's when you would use the M1B, or not M1B, the Boyle's law, Charles, and all those other guys.
STP.
No? It says it's at 300 Kelvin. So that's not STP.
Yeah.
So we are given the information of 300 Kelvin. We're given 1 liter of container, but we're given 500 milliliters of solvent or solution, right? So if we were to draw this out, basically what we have here is a closed container that's 1 liters in volume. Half of that is filled with a solution of 500 milliliters. So what is the volume for the gas?
500 milliliters. Oh, wait.
We are only given 2, we have a 1 liter container and a 500 milliliters solution. Where's our gas going to be found?
The area above.
Which has a volume of what?
500 milliliters.
So do we agree? Yeah, so he's right. So the gas flows out of solution, right? So all the gas is going to be in this area. While the solution, it's not going to be in the area that the solution is in, right? So the volume that the gas takes up is 500 milliliters, okay? As seen over there. So when we use our PV equals nRT equation, we're looking for pressure. E equals nRT over V. You know the moles is 0.499 moles. R is a constant. What is R?
It's 0.821.
David beat you to it, Nick, sorry. And then temperature is in Kelvin, which is 300 degrees or 300 Kelvin, right? If that had been in Celsius, we could just leave it as is, right? Yes, Nick?
Okay.
You're right, yeah. And then the volume was,
Doing it anyway, just like to be safe.
and then the volume is what, Nick?
4.5 liters.
Yeah, so it's, volume is gonna be in liters, not milliliters, so 0.5 liters. And if you put this into your wonderful, amazing calculator, what does one get? 24.6 atmosphere. That thing's probably gonna blow up. Getting ready to rupture. Okay. Any questions on this problem? This is a little bit of a tricky problem, just because people would immediately say 1 liter container, put that into their ideal gas equation. But you gotta think that this solution that you had there is not just gonna vanish, still there. So gas isn't gonna occupy all that area where the solution is.
Part was that, so like, understand that we needed to do limiting equation.
Okay, so like I always say is if you're given the information of, if there's 2 reactants and you're given the information of both of them, you need to calculate limiting reactants. If there's 3 reactants and you're given the information for 2 of them, and they say the other one's excess, or maybe you're given the information for all 3 of them, you have to calculate limiting reactant either way. So that's how I would just make it a point whenever you do these problems. And you have a reaction, more than 1 reactant. Am I given the information of both? Does it say that one of them is in excess? Like, be on the lookout for those things when you're practicing. All right, I think number 18 will be fine if you took a picture of those reactions earlier. Maybe if you can recall those. You want to take this? So number 18 encompasses the A, B, and yeah, just. I'll be walking around, so if you have questions, just raise your hand.
Or, yeah, wait, no. Because
Oh, SMS 10, sorry.
yeah, 10. That's a lot of.
That's correct, the salt, but. Six, right, plus 2. That's one of those that. Because the iron gas law is. So we only.
October something, 15th.
It was like one of the preseason. The tickets are only like $30.
Want to see Victor Wembanyama on the
Yeah.
Dominate.
Wemby. Did you see the Dame Lillard trade?
good.
That's,
That's wild.
yeah, Milwaukee's about to like come get in like the finals for sure. Make it to like the.
So the BR2.
I think so.
I think
They won the
so.
championship the year before.
Oh, yeah.
That was 2021. I think.
But they lost, right? Against the. Heat?
Yeah, yeah, yeah. Yeah, because they were the 1 seed, they were the 8 seed.
Yeah,
Are y'all ready to go over it?
Oh, no. Yeah, definitely.
All right, let's do it. So suppose a student mixes zinc metal, excess HBr solution. Have y'all supposed?
I suppose they'll end up with ink plus HBr equal to. Or plus H2.
Right, that is correct. So if you were to write out a balanced chemical equation of the reaction, that's Zn solid plus HBr. And as Nick said, it would be NBr2 and hydrogen 2. Let's fill in our physical states. HBr, strong acid, so it's aqueous. Zinc bromide, aqueous. What about H2?
Yes.
Yes, whole point we're doing this problem. All right. Is this balanced?
No.
How do I make it balanced?
The two. Like zinc.
So like. All right, let's see. Two hydrogens, we're good. Two zincs, good. Two bromines, 4 bromines, we're not good. Remember, zinc has a 2+ charge. It's always fixed at +2. So you do Zn 2+, and then Br minus. Or to do your little loop-de-loop method, Zn Br2. What that tells me here is that this should not be a 2. And if this shouldn't be a 2,
Then just delete the two by zinc.
let's see. So one zinc, y'all know the drill. Two hydrogens, two bromines. And overall, we're good. So this is what the balanced chemical equation of the reaction is. This right here. All right. Student collects the gas in a 4-liter container, measures the pressure to be 17 atmospheres, calculate the temperature of the gas. All right. So you have pressure, right? You have volume. R is obviously a constant, and then we don't have the moles we need yet, but we can find them. So what law do we need to use?
Avogadro's law?
Well, remember Avogadro's law is like before and after. So like you're given an initial number of moles or like an initial volume, and then you need to find like a final moles or a final volume.
And also, we're looking for temperature. Oh, T. Oh,
This would be a one-off only thing, like only one scenario given.
Moles and volume law?
That is Avogadro's law.
Oh.
But we have pressure, we have volume, we have R, and we have moles. So what law do we need to use? Yeah, the ideal gas law. So EV equals NRT. That's the law we need to use. Reason being, because we don't have an initial and a final. This is just everything lumped into one. This is one equation. All right, and we need to solve for the temperature here, but before we do that, there's 2.34 moles of zinc metal. How do I get from moles of zinc metal to the moles of hydrogen gas?
Molar ratio,
Which is what in this case?
1 to
1 to 1. So moles of Zn equals the moles of H2. So now we have everything we need to plug into our equation.
So you always try and find the gas.
Yeah, because again, this is the ideal gas law, so you can only do it with gases. So solve it out, right? So we're gonna try to solve for temperature here. So our pressure is 17 atmospheres. Our volume is 4 liters. Our moles, as we just determined, was 2.34. R is a constant, 0.0821 atmospheres, liters over moles Kelvin. And then temperature, T, that is what we're solving for. So if we plug this into our calculator, what will you get?
I did pressure times volume over moles times the constant. This is the same thing.
Yeah, it is the same thing as this.
I put 400 milliliters instead of 4 liters.
Tough. Remember that your volume,
65.
remember that your volume always has liters.
For this,
Yes.
for the gas law, it's always liters.
What'd you get?
65.
65?
Oh, 365.
365?
Calculate. I don't think that's right.
Wait a minute.
Well, it is Kelvin though, so
It is.
that makes sense actually.
Oh, let's see.
0.5.
Somewhere around 365. I wouldn't say 365, but
What's 365.54?
365, or okay, let me use like all the digits.
17 times 4 is 60.
59.6.
Wait, what? 78 times 4 is 68.
Wait, oh. I thought you were talking about the other.
No,
never mind, I was
17
gonna
times
say
4 is 60.
Oh, because you didn't put 17. Oh, so it's 0.0. Oh, that's why I did wrong.
17 times 4 is 68. 68 divided by 0.06754. You get from multiplying 2.34 times 0.0281 gives you 1,034. Might be wrong.
It's
What's 68 divided by?
so it's 0.0821.
I got 357.
Oh, I said 281, not 821. Yeah.
Yeah, but the answer I got was 353.96.
No, I got it wrong because I did
I got
281.
357.
Close. So 353.96. Let's go to like two decimal places on this. 353.96 Kelvin.
So if I got 357 on the exam, I'd be wrong. Like if it was a free response.
Oh, you should give you credit for like a variety of answers.
Okay. Cause I was like, I did all the math right, but I mean, let me try again. I don't know how I got that. Okay, now I got the right answer.
353.96?
Yeah.
Nice. All right, the correct answer is indeed 353.96 Kelvin. Any cues on this one? So that's a hip way to say questions, cues. All right, let's get to 20, because I don't think y'all done 19 yet. All right, a sample of Freon 12, which is, Freon 12, occupies 25.5 liters at 298 Kelvin and 143 kilopascals. And we want to find its volume, STP. Yeah. There's multiple ways of doing this. I'll let y'all know right now.
And runs out of ink, you don't have any other.
There's a certain way to do this. There's other way to do this.
Pascals.
Now, y'all need to remember the conversion.
Don't,
You do.
oh. It's nice.
That sounds about right.
0.3 is.
Well, 100 pascals equal
Times 10
like
to the fifth.
100,000.
One
Pascals.
point zero three six times.
That's for pascals.
Oh, so we're going the other way?
Yeah, this is for kilopascals. So you have to divide that number by 1,000.
Or you could just move it.
Yeah,
To the right.
Hmm?
You could just move it 3 to the right.
It'll be to the right or
It's
to the
gonna
left.
be- It's gonna be 14. It's like milliliters to liters.
Take 143.3 kilopascals multiplied by 10 to the power 3.
In 1 point.
Oh, you're doing it that way, okay. Yeah, what I did was, I'm just using the kilopascals and just running with it.
Yeah, that's what I was gonna do. I was like, cause I did kilopascals in my, in the calculation, I got it right.
As long as you get the right answer at the end of the day, it don't matter.
Moles. 3 on 12. Wait, molar mass times Avogadro.
What about Avogadro's number? Well, you don't need to do that. You can just use the certain law to get the moles.
Oh. Avogadro's mom. No, well, no, cause that's on 2 sides. We don't have 2 sides. Oh.
Remember I said you could do it multiple ways. Mercedes, Lamborghini, BMW, it don't matter. Don't matter. Toronto Raptors in 6. That's what I think.
Who do they even have out there? Even?
Everybody left.
Yeah, Pascal.
Pascal Siakam. Pascal.
I don't follow that.
He's alright. I don't think he's like a star player.
Yeah, you'd have to convert him to atmospheres. He'd be more effective that way.
Oh, that's nice.
There are multiple ways.
Oh, wait.
Let's skip 19.
Yeah, we did.
Why?
Cause I gotta show them the trick.
Oh, you gotta show them the trick.
We'll do 20 first and then go back to 19. Because 19 might be unfamiliar to some of you. You might be doing it the long way.
So this is what Mr. UT said last semester.
Oh, but he was, where was he? Like over here? He used to use a whiteboard back then, I think.
Wait, gold? They said.
Projector in his little yellow notebook from.
Yeah, that's right. Right. Do you all have an answer?
Forgot what standard.
1 ATM, 73 Kelvin.
Oh, yeah.
I mean, that's a standard temperature, you got the temperature part, and then pressure, you got the pressure part.
Pressure is.
The one for temperature and pressure is just 100 Kelvin and 1 ATM.
Yeah. Oh, well, but yeah, I'm still confused on our lovely moles. Oh, well, I guess it's two different ways first. So
You
first,
have to calculate how much carbon, chlorine, and chloride there is.
yeah,
There are two different ways. One, I see one room doing one way and the other room doing the other. Other side.
carbon's
It's like the Berlin Wall up here.
chlorine is
That is a terrible
34.
comparison.
Then I gotta be Reagan now. Gorbachev, tear down this wall.
Chlorine is 36.
All right, y'all got an answer now. All right, anyway, we're gonna go over it. So Freon 12, right, occupies 25.5 liters at 298 Kelvin and 143.3 kilopascals. Find its volume at STP. I'm gonna split this down the middle because, as I said before, there's two ways of doing this. So the first way is to use, what'd you do, David? Yep, that's one way to do it. So you could say P1 V1 over T1 was P2 V2 over T2. That is one way of doing it. We'll do it that way first. So sample of Freon 12 occupies 25.5 liters, 298 Kelvin, 143.3 kilopascals. So what I like to do first, you don't have to do this, but me personally, I like to convert all my stuff to atmospheres before starting the problem. So 143 kilopascals. And there's 101.
Oh, actually, it's 143 point.
Oh, yeah. I had to be that guy, but yeah, that's good that you corrected me. Thanks. 101.325 kilopascals for every 1 atmosphere. So when we solve this out, you will get 143.3 divided by 101.325. Okay, I typed in 5. All right, divided by 101.5. All right, you should get approximately 1.41 atmospheres. Now we can plug this in. So 1.41 is our initial pressure, 25.5 is our initial volume, 298 is our initial temperature, and we're solving for the volume here. So we're solving for V2 essentially. So what's STP again? Like what are the
One
things?
ATM and 73 Kelvin.
Yeah, 1 ATM, and this is V2, and then this is 273 Kelvin. So if we solve for V2 using our calculator, we're gonna do some cross multiplication here first.
Just one by each side.
So 1.41 times 25.5 times 1.41 times 25.5 times 273, get a certain number, and we're gonna divide that by 298. And our V2 should be 32.94. All right, so that's one way of doing it. This is the second. What you also could have done is you could have used the ideal gas. So EV equals nRT. Then now we're gonna find our moles first. We're gonna find our moles of Freon 12. Because I remember there's a little shortcut you could use. Go from moles to liters. So let's do that. So if we do that, that's 1.41 atmospheres again, times our volume 25.5 equals our number of moles here, which is N, R is a constant, 0.0821 times temperature 298. So all that, 1.41 times 25.5. Divide that by certain number of 0.0821 times 298. And moles here should be approximately 1.47. 3 on 12. How do we get from moles to liters at STP? So for every 1 mole, there is 22.4 liters. So if you multiply this times 22.4, look at that, you get
Moles of it, or liters.
32.92. Chemistry works.
And just to be
Figure
clear,
this out.
the 22.4 liters per mole only applies for gases that are at STP. So that's why we could utilize that.
That's the only reason we did this, because it says STP. In any other instance, that wouldn't apply.
Everyone you prefer.
I mean, that's, yeah, whichever one you prefer. Like, I did it the second way, but if you like the first way, that's fine too. Yeah. If we're going based on technicalities, in the problem, there's 3 sig figs, right? So the final answer should have 3. But the thing is, like this unit moving forward, he doesn't really care about sig figs too much. Like if you're at like 3 or 4, it's generally fine. Like for me, I go to like 2 or 3 decimals. All a day.
Feels good.
All right.
Yeah, I want to do number 19. And we'll call it.
Right. Dylan is now going to show you all the magic method for number 19. Okay.
Good go, Dylan.
Thanks. All right. So calculate the density of oxygen gas at 453 Kelvin and 0.75 atmospheres. So density of a gas is always going to have certain units. Do we remember what those units are?
That's mass over volume.
No.
Of properties of a gas.
So yes, it's mass over volume, but specifically what are the units? Because mass can be in microgram.
Gram over liters.
Yeah, so gram per liter is the unit of a gas, okay? So we're asked to calculate the density of O2 gas. Well, we know that density equals mass divided by volume, right? So you may be wondering, how do I get to this? How do I put any information about the temperature and pressure into this equation?
Well, you know that the mass of oxygen is.
How did you get there?
32. Of
Yeah.
oxygen.
That's what I'm gonna do after I derive the equation. So the equation we're gonna use is the ideal gas equation. That one relates temperature, pressure, and volume. Okay. So PV equals nRT. But what do we know about moles? What is moles equal to?
Mass over molar mass.
Yes, so mass divided by molar mass, right? So this is just basic substitution, right? We can insert mass divided by molar mass in for N because that equals N, right? So if we do that, we get PV equals mass times RT over molar mass. But now look what we have here. Density equals mass divided by volume. Now we have mass and volume in the same equation. So how could we find density? If density equals mass divided by volume,
Divide each side by volume.
yeah, so if we want to if we want to solve for M over V, that means we have to isolate those to one side. Okay, so if we multiply both sides by molar mass, we get P times V times molar mass equals MRT. But remember, the variables we're looking for is for M over V, right? So now we need to divide both sides by RT. Will give us M equals P times V times molar mass over RT. So now look at where our units are. We just need to get V to the other side, and we just do that by dividing by volume. So we get M over V equals pressure times the molar mass of the gas times RT. So this is how you derive the equation. And we know that our density, we said, is equal to mass divided by volume. We've known that since back in middle school, right? So you can say that E is equal to M over V, which is equal to pressure times the molar mass over RT. So based on this principle, if we just take this up here, we can say density of the gas equals P times molar mass over RT. We have all the information to calculate that.
0.75 ATM times 32 divided by 1 time.
Hold on. Let's work on this together, man. All right, so let's just plug everything in. Yes, pressure is 0.75 ATM, 32 grams per mole because oxygen is a diatomic gas.
Over 0.081.
What are the units?
That's a good question.
Everyone always knows the number.
Liters.
Everyone always forgets the units.
ATM
Yeah?
over, oh yeah, is it that?
No?
Over, hold on. Over, wait, what is that?
Moles times Kelvin.
Oh, moles.
And then the temperature was 450
Or,
Kelvin. Look at all these wonderful units cancel out. That will cancel there, this will cancel here, that will go there. We have the liters in the denominator, which is what we need, and we have mass in the numerator, which is what we need, grams over liters. That checks out. What is the density of the oxygen at this temperature? What?
yeah, 389.76.
389.
77.
Do a 0.8 grams per liter. So I hope the derivation wasn't too, I tried to make it flow kind of like M&M so you could get it and, you know, see what we're doing.
Actually, no.
But now what I suggest doing is just adding this equation here to one of your as one of your tools in your toolbox, so you don't have to do this every time. You know that the density equals M over V times this over that. Then you can just go straight to that equation. You don't have to do this every time.
Because a lot of stuff.
All right, so who's gonna memorize this by Monday?
That does not seem right.
It's not that hard to remember. So,
All right, hold on, Nick. Someone got a different answer than you. Yeah, that's a big difference.
If we do it.
All right, gotta whip out the phone.
Honestly, your answer seems right. On a precursor glance.
I know what I did. I did the Apple
Oh,
calculator.
yeah, definitely. I just did Apple Calculator too. I'm just kidding. All right, yeah, so the answer was just a little bit off, 0.64 grams per liter.
And that's just a little off.
Yeah, can't guarantee you, Nick, that we would accept that on the test, just
Oh,
even though it's a
okay.
little off.
It was the same sig base, no, almost, well, it was like.
Actually, it was
Oh.
a lot,
Uh,
that was wrong too. But that's okay.
No, yeah, I